What is the difference between Euclidean and Manhattan distance formula? Imagine you're trying to find the quickest way to walk from one corner of a city block to another. Would you walk straight across or follow the streets? That's the core idea behind understanding the difference between Euclidean and Manhattan distances. Both are ways to measure how far apart two points are in coordinate systems, but they do it in different ways based on the path taken. Euclidean distance is like flying directly from one point to another in a straight line. It's the shortest path between 2 points, just like how a bird might fly across a field. To calculate this, you use the Pythagorean theorem. For 2 points, say, x1, y1, and x2, y2, the Euclidean distance is found by taking the square root of the sum of the squares of the differences in each coordinate. So it looks like this. The square root of x2, x1, 2 plus y2, y1, 2. If you're working in 3 dimensions, you just add the difference in the third coordinate, square it, and include it under the square root. This method gives you the true straight line distance, which is perfect for many applications like physics, geometry, and machine learning. Now think about walking through a city laid out in a grid. You can only move along the streets, which run horizontally and vertically. The distance you travel in this case is called the Manhattan distance, named after the grid-like streets of Manhattan in New York City. To find this, you add up the absolute differences of the coordinates. For the same points, it's the absolute value of x2, x1 plus the absolute value of y2, y1. This method measures the total distance you would walk if you had to stay on the grid, turning at right angles at each intersection. It's especially useful in city navigation, robotics, and computer algorithms where movement is restricted to certain directions. The key difference is how they measure distance. Euclidean distance finds the shortest straight line between points, which makes it sensitive to large differences in any coordinate. Manhattan distance, on the other hand, sums the differences along each axis, making it more suitable when movement is constrained to grid-like paths. Both formulas are special cases of a more general distance called Minkowski distance, where the parameter p determines the type of distance. When p equals 2, you get the Euclidean distance, and when p equals 1, you get the Manhattan distance. In coordinate geometry, understanding both distances helps you analyze shapes, paths, and spatial relationships from different angles. Whether you're calculating the true geometric distance between points or modeling movement along city streets, knowing these formulas helps you see the world in a more flexible way.